Welcome. In this lecture, we shall calculate the area moment of inertia for some complex cross-section shapes about the respective centroidal or neutral axis. The steps to calculate the area moment of inertia about the centroidal or neutral axis for complex shapes are: find the centroid of the complex shape, which is but a combination of basic planar shapes, and add the moment of inertia of each basic shape about the centroidal or neutral axis of the whole section to calculate the net moment of inertia. Before we take up some examples for finding the moment of inertia of some complex shaped sections, it is worth noting a point that somehow got missed in the last lecture. One of the assumptions we made during the derivation of the flexure formula was that the sections are symmetric about the vertical y-y axis or vertical plane passing through the centroid, or with respect to the load applied. If this would not have been the case and the section was unsymmetric about the vertical plane passing through the centroid, then the horizontal beam would not simply bend but would be associated with twisting about the horizontal z or polar axis due to the shifting of an imaginary point called the shear center from the centroid to some location offset along the x-axis or horizontal axis. The shear center is the point where a load can be applied such that the beam only bends with no twisting. We shall deal with only symmetric beams, the symmetry being with respect to the vertical plane passing through the centroid for calculating the bending and shear stresses in later chapters. As such, for this chapter dealing with the calculation of area moment of inertia alone, we shall consider both symmetric and unsymmetric sections though. Without any proof, let us understand how to calculate the centroid of a complex cross-section shape consisting of n basic shapes. From some assumed position of the origin of Cartesian coordinate system as the reference, let x1, x2, x3 and so on till xn denote the horizontal distance of the centroid of each basic shape respectively, where n is the number of basic shapes making the complex cross-section. Likewise, y1, y2, y3 and so on till yn denote the vertical distance of the centroid of each basic shape from the origin. Now the horizontal distance of the centroid of the complex shape from the origin is given by summation of the product of area and horizontal distance of centroid of each basic shape from the origin divided by the total area of the complex shape. In symbolic notation, it is given by x bar equals summation of ai times xi over summation of ai, where the index I ranges from 1 to n in both cases. Likewise, y bar equals summation of ai times yi over summation of ai, where index I ranges from 1 to n in both cases. Let's take the first and very simple example given by a hollow rectangular cross-section, the dimensions of which are shown here. It is easy to make out by inspection and from symmetry along the horizontal and vertical planes that the centroid C should be at a distance of 80 mm to the right and 100 mm above the bottom left corner of the section. Still, let us try calculating the centroid by applying the formula as discussed. Let us name the bigger rectangle as 1 and the smaller rectangle as 2. Let us also assume the origin of the Cartesian coordinate system at the left bottom corner as the reference from where the distances will be measured. We have x bar equals a1 times x1 minus a2 times x2, the whole divided by a1 minus a2. Here we have used minus sign instead of plus for the smaller rectangle on both numerator and denominator, since it is being removed from the bigger rectangle and not simply added up to create the complex shape. Hence x bar equals 200 times 160, which is area 1, times 80, minus 160 times 120, which is area 2 times 80, the whole divided by 200 times 160 minus 160 times 120, which comes out to be 80 millimeters. Likewise, y bar can be found on a similar note and comes out to be 100 millimeters as understood earlier. Let us now consider another example. The given figure has three basic shapes and all areas are added together to form the complex shape. The horizontal distance of the centroid of the whole section from the reference y-axis, that is x bar, is found to be 2.729 units. Similarly, the vertical distance of the centroid of the whole section from the reference x-axis, that is y bar, is found to be 1.3397 units. You may pause the video at this instant and observe the values being used for more clarity. The values of the centroid may be rounded up to 2 decimal places for convenience. Now that we know how to calculate the position of the centroid for a complex section, it's time to calculate the area moment of inertia about the centroidal or neutral axis. Here, we shall make use of the parallel axis or transfer axis theorem extensively to transfer the area moment of inertia of a basic shape from its own centroid to the parallel axis passing through the centroid of the whole section. By definition, it is given by I about any other axis parallel to the centroidal axis equals I about the centroidal axis plus the product of the area and the square of the distance between the two parallel axes. Let's consider the same example that we have referred to for finding the area moment of inertia about the centroidal axis. For this example, one may use the formula for finding the moment of inertia of a semicircle about the centroidal axis parallel to its base, that is the diameter, as 0.11 times r to the power of 4, which may also be worked out from the basic principles instead of memorizing by heart. Now, I about the horizontal centroidal axis, that is the x-axis, is calculated as shown. You may pause the video for a moment to comprehend the usage of different values and resume when understood fully. The area moment of inertia about x-axis is hence calculated as 9.502 in length units to the power of 4. Similarly, the I about the vertical centroidal axis, that is the y-axis, is calculated and is found as 31.537 in length units to the power of 4. Again, the video may be paused here briefly to comprehend the usage of various values. In the next few lectures, we shall consider solving some numericals to calculate the bending stresses set up in beams.